Doo-doo-doo. Oh, look at this. Oh shit, what is this noise? Start now, guys. Start now. Start now. Go to the gym. What else? Otherwise, a kettlebell will show up into your nightmare. And we love gym. No, this one. Okay, what do I want? Wait! Okay, got it. I want to watch today. You know, I'm not a person who watches usually. I'm a person who other people watch. But today I want to watch Andrew NG with his crazy stories about the world of ML, machine learning, XGBoost, you name it. Let's go, guys. XGBoost, XGBoost, XGBoost. Random forest. Oh shit. What is this? They have a course on Control Shift 2. So they have a, yeah. Most effective leader. They have a course on OpenAI. Oh, that's cool. I want to know that. Wow.
What would you recommend? How do they go about day-to-day sort of
Again,
specific
this guy.
advice
Fuck
about
off.
learning in the world of deep learning, machine learning?
Not your business. Okay, actually, why am I such an asshole? I saw Lex Friedman in Jiu-Jitsu. Like,
Now we have
our
Kiara.
kickboxing session was finished, and he entered, like, after kickboxing it was jiu-jitsu, so he entered the wrestling room, and I just said, oh, Lex Friedman. Like, I haven't seen him in person before, but I knew, like, of him from YouTube. Automatically like, what is this word, tried to shake his hand, and he was very friendly. So what I am pissed off is that, dude, I have another Google account, and that's all Lex Friedman. I don't want these people to show up in this in this one, you know. So let's see what's up with OpenAI, huh? And then let's start watching. Like, this is distraction for sure, but a good distraction. We don't have good distraction, guys. I am bullshitting. Playlist, that's what I should do. I should go here right away. But I'm curious to know about OpenAI. Wait, why are we here? Stanford. And then, ooh, look at us, guys.
Welcome to CS229 Machine Learning.
ML models
When
and
we
errors.
train this.
Okay, let's watch this. Oh, this guy is from OpenAI. Again, 2022, they have another machine learning course. That's pretty, like 21 hours ago, okay? These are just designed for us. Videos, let's see what's up. Pre-training, oh, that's nice. That was actually the question we had. How much it takes, how much money they are paying about their dataset trainings. All of them are on large language model. Dude, I know I'm learning machine learning, but in a second, like, nobody cares about machine learning anymore. I need to adapt fast. Let's watch this one.
Give a talk. So he's currently a research scientist on the OpenAI ChatGPT team. He has worked on various aspects of large language models. Things like pre-training, instruction fine-tuning, reinforcement learning with human feedback, reasoning,
What am I doing?
and so
Never
forth.
open that
And some of
again.
his notable works include the scaling FLAN papers such as FLAN T5, as well as FLAN POM, and T5X, the training framework used to train the POM language model. And before OpenAI, he was at Google Brain, and he received his PhD from MIT. So give a hand for
Shit,
Hyung-won.
he was at MIT. Google Brain.
All right, my name is Hyung-won, and really happy to be here today.
Why is he
And this
here?
week I was thinking about, by the way, is mic working fine? Yeah, so this week I thought about, okay, I'm giving a lecture on Transformers at Stanford. What should I talk about? And I thought, okay, some of you in this room and in Zoom will actually go shape the future of AI. So maybe I should talk about that. It's a really important goal and ambitious, and we really have to get it right. So that could be a good topic to think about. And when we talk about something into the future, the best place to get an advice is to look into the history. And in particular, we'll look at the early history of Transformer and try to learn many lessons from there. And the goal will be to develop a unified perspective in which we can look into many seemingly disjoint events. And from that, we can probably hope to project into the future what might be coming. And so that will be the goal of this lecture, and we'll look at some of the architectures of the Transformers. So let's get started.
Dude, I hope Stanford doesn't tell me that, okay, you are copyright issues. Dude, you know that. This is a Stanford, guys. Just
AI is so advancing so fast that it's so hard to keep up. And it doesn't matter if you have like years of experience, there's so many things are coming out every week that it's just hard to keep up. And I do see many people spend a lot of time and energy catching up with this latest developments, the cutting edge and the newest thing, and then not enough attention goes into old things because they become deprecated and no longer relevant. But I think it's important actually to look into that, because we really need to, when things are moving so fast beyond our ability to catch up, what we need to do is study the change itself. And that means we can look back at the previous things and then study the difference, because taking a lot of time and energy.
That's interesting. So when things are changing fast, we need to study the change itself. Let me check my email address, how many strikes I received from YouTube so far. Okay, nothing.
Energy catching up with this latest developments, the cutting edge and the newest thing, and then not enough attention goes into old things because they become deprecated and no longer relevant. But I think it's important actually to look into that, because we really need to, when things are moving so fast beyond our ability to catch up, what we need to do is study the change itself. And that means we can look back at the previous things and then look at the current thing and try to map how we got here, and from which we can look into where we are heading towards. So what does it mean to study the change itself? First, we need to identify the dominant driving forces behind the change. So here, dominant is an important word because typically a change has many, many driving forces, and we only care about the dominant one because we're not trying to get really accurate. We just want to have the sense of directionality.
This guy understands. That's it. That's the power you get when you, after MIT, you go Google Brain and now you're OpenAI. That's wisdom talking, you know? It says, we don't want to have an accurate solution. Fuck mathematics.
Second, because typically a change has many, many driving forces, and we only care about the dominant one because we're not trying to get really accurate. We just want to have the sense of directionality. Second, we need to understand the driving force really well, and then after that we can predict the future.
So first, identify the dominant driving force, then understand it, then predict the dominant. Fuck off!
Trajectory by, I don't know, rolling out the driving force and so on. And you heard that right. I mentioned about predicting the future. This is a computer science class, not like an astrology or something. But we do, I think it's actually not that impossible to predict some future trajectory of a very narrow scientific domain. And that endeavor is really useful to do. Because let's say you do all these and then make your prediction accuracy from 1% to 10%. And then you make, say, 100 predictions. 10 of them will be correct. Say one of them will be really, really correct, meaning it will have an outside impact that outweighs everything.
Yeah.
And I think that is kind of how I've seen it, many general things.
That was actually also
that
beautiful.
You really have to be right.
Right? He said, not all of them, like you have some future prediction trajectories, 100, 10 of them will be kind of correct, and one of them will be very good, and that's enough for us. I like his mindset.
A few times. So, why? So if we think about why predicting the future is difficult, or maybe even think about the extreme case where we can only do the prediction with perfect accuracy, almost perfect
Stanford
accuracy. So here I'm going to do a very simple experiment of dropping this pen and
course
follow
on
this
transformers.
same three-step process. So we're going to
Maybe
identify the
after the machine learning,
dominant driving
we need to
force.
watch this
First
one.
of all, what are the driving forces acting on this pen? Gravity downwards. And is that all? We also have like say air friction, right? If I drop it, and that will cause what's called a drag force acting upwards. And actually, depending on how I drop this, the orientation, the aerodynamic interaction will be so complicated that we don't currently have any analytical way of modeling that. We can do it with the CFD, the computational fluid dynamics, but it will be non-trivial. So we can neglect that. This is happy enough that gravity is probably the only dominant force. So we simplify the problem. Second, do we understand this dominant driving force, which is gravity? And we do, because we have this Newtonian mechanics, which provides reasonably good model. And then with that, we can predict the future trajectory of this pen. And if you remember from this dynamics class, if we have this initial velocity is 0, I'm not going to put any velocity, and then let's say position is 0 here, and then 1/2 GT squared will give a precise trajectory of this pen as I drop this. So if there is a driving force, single driving force, that we really understand, it's actually possible to predict what's going to happen. So then why do we really fear about predicting the future in the most general sense? And I argue that among many reasons, the number of driving force, the sheer number of dominant driving forces acting on the general prediction is so complicated, and their interaction creates a complexity that we cannot predict the most general sense. So here's my cartoon way of thinking about the prediction of future. X-axis, we have a number of dominant driving forces. Y-axis, we have a prediction difficulty. So on the left-hand side, we have a dropping of pen. It's a very simple case. It's a difficulty is very small. You just need to learn physics. And then as you add more stuff, it just becomes impossible. So how does this fit into the AI research? And you might think, okay, I see all the time things are coming in, and we are bombarded by new things, and some people will come up with a new agent, new modality, new MMLU score, whatever. We just see so many things. It just, I'm not even able to catch up with the latest thing. How can I even hope to predict the future of the AI research? But I argue that it's actually simpler, because there is a dominant driving force that is governing a lot, if any, if not all, of the AI research. And because of that, I would like to point out that it's actually closer to the left than to the right than we actually may perceive. So what is that driving force? Maybe before that, I'd like to caveat that when I do this kind of talk, I would like to not focus too much on the technical stuff, which you can probably do better in your own time, but rather I want to share how I think. And for that, I want to share how my opinion as is, and so it will be very strongly opinionated. And by no means I'm saying this is which you can probably do. So what is that driving force? Oh, maybe before that, I would like to caveat that when I do this kind of talk, I would like to not focus too much on the technical stuff, which you can probably...
I like that. I like it. Fuck technical stuff. That's how I present too. Technical stuff, go grab a paper and
do better in your own time, but rather I want to share how I think. And for that...
That's nice. I want to share how I think.
I want to share how my opinion as is, and so it will be very strongly opinionated. And I'm by no means I'm saying this is correct or not. Just wanted to share my perspective. So coming back to this driving force for AI, what is that dominant driving force? And here's a plot from Rich Sutton, and on the y-axis we have the calculations plot. If you pay $100, and how much computing power do you get? And it's in log scale. And then x-axis we have a time of more than 100 years. So this is actually more than like exponential. And I don't know any trend that is as strong and as long-lasting as this one. So whenever I see this kind of thing, I should say, okay, I should not compete with this, and better, I should try to leverage as much as possible. And
interesting.
So what this means is you get 10x more compute every 5 years if you spend the same amount of dollar. And so, in other words, you get the cost of compute is going down exponentially. And this and associated scaling is really dominating the AI research. And that is somewhat hard to take, but that is, I think, really important to think about. So coming back to this AI research, how is this exponentially cheaper compute drive the AI research? Let's think about the job of the AI researchers. It is to teach machines how to think in a very general sense. And one somewhat, unfortunately common approach is we think about how we teach machine how we think. So meaning we model how we think and then try to incorporate that into some kind of mathematical model and teach that. And now the question is, do we understand how we think at the very low level? I don't think we do. I have no idea what's going on. So it's fundamentally flawed in the sense that we're trying to model something that we have no idea about.
Why? No, that's stupid. I don't agree. If we don't know something, still we have some ideas about.
What happens if we go with this kind of approach is that it poses a structure that serves as a shortcut in the short term. And so you can maybe get a paper or something, but then it becomes a bottleneck because we don't know how this will limit further scaling up. More fundamentally, what this is doing is we are limiting the degree of freedom we are giving to the machines, and that will backfire at some point. And this has been
whenever it
going
comes,
on for
we will get it.
decades. And bitter lesson is, I think, the single most important piece of writing in AI. And it says, this is my wording by the way, past 70 years of entire AI research can be summarized into developing progressively more general method with weaker modeling assumptions or inductive biases and add more data and compute, in other words, scale up. And that has been the recipe of entire AI research, not fancy things. And if you think about this, the models of 2000 is a lot more difficult than what we use now. And so it's much easier to get into AI nowadays from technical perspective. So this is, I think, really the key information. We have this compute cost is going down exponentially, and it's getting cheaper faster than we're becoming a better researcher. So don't compete with that, and just try to leverage that as much as possible. And that is the... driving force that
Who
I
is
wanted
competing
to
with that?
identify. And I'm not saying this is the only driving force, but this is the dominant driving force, so we can probably neglect the other ones. So here's a graphical version of that. X-axis, we have a compute. Y-axis, we have a performance of some kind. Let's think about some general intelligence. And let's look at two different methods. One with more structure, more modeling assumptions, fancier math, whatever. And then the other one is a less structure. What you see is typically you start with
Fancier
a
math.
performance
Did you see
when
that?
you have a low compute regime. And then, but it plateaus because of some kind of structure backfiring in structure. What you see is typical. And so it's much easier to.
Don't make it mental masturbation. Math is not needed, to be honest. We don't need math much more anymore.
Get into AI nowadays from technical perspective. So this is, I think, really the key information. We have this compute cost is going down exponentially, and it's getting cheaper faster than we're becoming a better researcher. So don't compete with that and just try to.
Yeah, oh, that's so nice. He's saying so nice things. He says, dude, we are getting the research from this computing stuff. Don't compete. Some people don't want to use, okay, they're okay using calculators, but a lot of people want to have proof for everything. It's just, dude, we can plot a graph, learn from that. They want everything to be proven in mathematics. Fuck that.
So this is, I think, really the key information. We have this compute cost is going down exponentially.
This is my guy.
And it's
getting
cheaper faster than we're becoming a better researcher.
We are becoming a better researcher. Dude, let the fucking chat GPT publish the paper. Write the sentences, stupid sentences. Who cares?
Compete with that.
Nobody
just try
reads.
to leverage that as much as possible. And that
Yeah, we need to leverage these tools as much as
is
possible.
the driving force that I wanted to identify. And I'm not saying this is the only driving force.
It's stupid. If MIT says you're not allowed to use chat GPT to write your thesis, I think that's stupid. Well, what is wrong if it helps me with writing it? And I am supervising it.
But this is the dominant driving force, so we can probably neglect the other ones. So here's a graphical version of that. X-axis, we have a compute. Y-axis, we have a performance of some kind. Let's think about some general intelligence. And let's look at two different methods. One with more structure, more modeling assumptions, fancier math, whatever. And then the
More modeling assumption. You don't want to have a lot of assumptions.
other one is a less structure. What you see is typically you start with a better performance when you have a low compute regime. And then, but it plateaus because of some kind of structure backfiring. And then with the less structure, because we give a lot more freedom to the model, it doesn't work at the beginning, but then as we add more compute, it starts working, and then it gets
Data,
better.
does it
We
mean?
call this more scalable methods. So does that mean we should just go with the least structure, most freedom to the model possible way from the get-go? And the answer is obviously no. Let's think about even less structure case. This red one here is it will pick up a lot later and requires a lot more compute. So it really depends on where we are. We cannot indefinitely wait for the most general case. And so let's think about the case
Even less structure.
What you see is
so whenever we have more data, we want to have less. At the beginning, that's actually very right. That's very smart. I think we can get the envelope of these curves. At the beginning, we don't have a lot of data. So, okay, we need to use our brain, come up with models and assumptions, right? This is just, at the beginning, we want to be assumptive. Then we get to a model that it gives us a beginning point to work with, and then we can use that model, primitive model, build, and now we gather some data. We have some of those data. Now we need to update. The game that brought us from beginner to intermediate doesn't take us from to intermediate to advanced. Now we need to destroy that mental model that we had, use the data we gathered, start a new model with the more data, less structure, build a new model, but gather more data, remove those assumptions that we had at the beginning, another one. That is smart. I love it.
You start with a better performance when you have a low compute regime. And
This
then
is
but it
super
plateaus
smart.
because
Yeah,
of some
that's
kind of
it.
structure backfiring. And then with the less structure, because we give a lot more freedom to the model, it doesn't work at the beginning. But then as we add more compute, it starts working.
What
and
is
then
compute?
It gets better. We call this more scalable method. So does that mean we should just go with the least structure, most freedom to the model possible way from the get-go? And the
Dude,
answer is
computer
obviously
science
no.
is beautiful.
Let's think about
Just we are wasting our time over mathematics and game theory.
even less structured case. This red one here is it will pick up a lot later and requires a lot more compute. So it really depends on where we are. We cannot indefinitely wait for the most general case. And so let's think about the case where our compute situation is at this dotted line. If we're here, we should choose this less structured one as opposed to this even less structured one, because the other one doesn't really work and the other one works. But crucially, we need to remember that we are adding some structure because we don't have compute, so we need to remove that later. And
Yes,
so-
whenever we don't have compute, we add structure. Structure or assumption.
So the difference between these two methods is that additional
This
inductive
was
biases or
beautiful. I
structure
loved
we
it.
impose, someone imposed, that typically don't get removed.
Thanks to Stanford for sharing this
Adding
video.
this, what that means is that at the given level of compute, data, algorithmic development, and architecture that we have, there's like an optimal inductive bias or structure that we can add to the problem to make the progress. And that has been really how we have made so much progress. But these are like shortcuts that hinder further scaling later on. So we have to remove them later on.
Yeah,
When we have-
once we got enough. What was that? Every revolution kills its children, something like that, right? Once we made it like, yeah, the same thing. The game that took us from beginner to intermediate doesn't take us from intermediate to advanced. Like those assumptions at the beginning gave us some force, but now we need to remove them to get more freedom. Damn, this is beautiful. Okay.
more compute, better algorithm, or whatever. And as a community, we do adding structure very well. And because there's an incentive structure with like papers, you add a nice one.
I love you. Okay. Dude, having this speech in Stanford, that was so nice. You pissed on everybody's face, actually. Good job.
And then you get a paper. But removing that doesn't really get you much. So that we don't really do that. And I think we should do a lot more of those. So maybe another implication of this bitter lesson is that because of this, what is better in the long term
wanna save
almost
this video
necessarily
somewhere.
looks worse now. And
On
this
my
is
other
quite
Google-
unique to AI research because the AI research of current paradigm is learning-based method, meaning that we are giving models freedom, the machines choose how they learn. So because we need to give more freedom, it gives it's more chaotic at the beginning, so it doesn't work. But then when it started working, we can put in more compute, and then it can be better. So it's really important to have this in mind. So to summarize, we have identified this dominant driving force behind the AI research, and that is this exponentially cheaper compute and associated scaling up. Now that we have identified, if you remember back from my initial slides, the next step is to understand this driving force better. And so that we're going to spend most of the time doing that. And for that, we need to go back to some history of Transformer, because this is a Transformers class, and analyze key structures and decisions that were made by the researchers at the time, and
Oh, you
why
want
they
to
did that.
remove those
Whether there was an
Transformer
optimal structure
assumptions?
that could have been added at the time, and why they might be irrelevant
Dude,
now.
oh my god, I haven't learned machine learning yet. They're saying machine learning is not fucked up. Transformers, we used it to make LLM. Now we need to get rid of Transformers. Wow.
And should we remove that? And we'll go through some of the practice of this, and hopefully this will give you some.
That
sense
was
of what,
beautiful. Studying the
scaling
change. That was
research
nice.
Looks like. So now we'll go into a little bit of the technical stuff. Transformer architecture. There are some.
This fucking shit find the equilibrium. Fuck you and your equilibrium, Von Neumann or whoever the fuck you are. That's if we have data, we can see people act on a line, we can define our new equilibriums. Fuck mathematics.
I'll talk about
game theory is not mathematics. Fuck you.
3 of them. First is the encoder-decoder, which is the original transformer, which has a little bit more structure. Second one is the encoder only, which is popularized by Bert. And then third one is decoder only, which you can think of as a current, like GPT-3 or other language models. This has a lot less structure than the encoder-decoder. So these are the 3 types we'll go into detail. Second, the encoder only is actually not that useful in the most general sense. It still has some place, but we will just briefly go over that and then spend most of the time comparing 1 and 3. So 1 has more structure. What's the implication of that, and so on. So first of all, let's think about what a transformer is. Just at a very high level, or first principles, what is a transformer? It's a sequence model. And sequence model has an input of a sequence. So sequence can be, sequence of elements can be words or images or whatever. It's a very general concept. In this particular example, I'll show you with the words. Sentence is a sequence of words. And then the first step is to tokenize it, because we have to represent this word in computers, which requires just some kind of a encoding scheme. So we just do it with a fixed number of integers that we have now, a sequence of integers. And then the dominant paradigm nowadays is to represent each sequence element as a vector, dense vector, because we know how to multiply them well. And then so we have a sequence of vectors. And finally, this sequence model will do the following. We just want to model the interaction between sequence elements. And we do that by let them take the dot product of each other. And if the dot product is high, we can say semantically they are more related than the dot products that is low. And that's kind of the sequence model. And the transformer is a particular type of sequence model that uses what's called attention to model this interaction. So let's get into the details of this encoder-decoder, which was the original transformer. It's quite many, many pieces. So let's go into a little bit, a piece at a time. So starting with the encoder. So here I'm going to show you an example of machine translation, which used to be very cool thing. And so you have an English sentence that is good, and then we're going to translate into German. So first thing is to encode this into a dense vector. So here I'm representing it with this like vector size 3 or something. And then we have to let them take the dot product. So this lines represent which element can talk to which element, other elements.
Stanford
here, because it's an input, we take what is called a bidirectional attention.
Android is 4 years ago, this video is
and then we have this NLP or feed-forward layer, which is per token. It doesn't have any interaction. We just do some, some multiplication just because we can do it. And then that's one layer, and we repeat that n times, and that's just the transformer encoder. And at the end, what you get is the sequence of vectors.
Go watch it from Stanford.
The sequence
no, don't go watch
in this case, a word. So that's the output of this encoder. Now let's look at the decoder, which is similarly shaped stack of layers. So here we put in as an input what the answer should be. So here DOS is the beginning of sequence, and then das ist gut. I don't know how to pronounce it, but that's the German translation of that is good. And so we kind of go through the similar process. Here we have a causal self-attention, meaning that the tokens of time step t can only attend to t and before. Because when we start generating it, we don't have the future tokens. So we cannot, when we train it, we should limit that. And that way, this is done by like masking, but it's just different from the encoder. So after this, you can get, after, again, n layers, you get this sequence output, and you have this, the output is sequence. So sequence to sequence mapping, this is a general encoder-decoder architecture. And when you get this end of sequence, you stop generating it. So this is the overall picture. Now I'll point out some important attention patterns. So we are translating into German what is input to the encoder. So there has to be some connection between the decoder and the encoder that is done by this cross-attention mechanism shown in this red, which is just that each vector's representation of each sequence in the output decoder should attend to some of them.
Fuck off. All right, go ahead.
I will come back to the implication of this design. So, yep, that's that. And now move on to the second type of architecture, which is encoder only. We'll spend a little bit of time here. So again, we have we have the same input, and we go through similar structure. And then in this case, the final output is a single vector. Regardless of the length of the sequence, we just get a single vector. And that is that represent the input sequence. That's a dense vector representation. And then let's say we do some kind of a sentiment analysis. We run through a task-specific linear layer to map it to classification labels, positive or negative probabilities here. And that's required for all these task-specific cases. And this is kind of popularized by BERT. And what this means is that here at the time, 2018, when BERT came out, we had the benchmark called GLUE, which was a language understanding task. You have a sequence in, classification labels out for most cases. This was how the field really advanced at the time. So when we care about such tasks, then there's an incentive to think about simplifying the problem, adding the structure to the problem so that we can make a progress. So the additional structure that was put into this particular architecture is that we're going to give up on the generation. If we do that, it becomes a lot simpler problem. Instead of sequence to sequence, we're talking about sequence to classification labels, and that's just so much easier. And so at some point, 2018, 2019, a lot of the papers are just, research was like, we sometimes call it BERT engineers. It's a little bit change of something, get like 0.5% better on glue, and you get a paper and things like that. It was like very chaotic era. But if you look at from this perspective, we are putting the sequence structure of not generating the sequence. That puts a lot of performance win, but in the long term, it's not really useful. So we're not going to look at this encoder-only architecture going forward. Third architecture, decoder only. This one is my favorite personally, and it looks kind of daunting, but because of this attention pattern, but it actually is very simple. So here we only have a single stack, and it can actually generate stuff. And so there's misconception that some people think this decoder-only architecture is used for language modeling next to prediction, so it cannot be used for supervised learning. But here, we can actually do it. The trick is to have this input that is good concatenated with the target. And if you do that, then it just becomes simple to sequence in, sequence out. So what we do is the self-attention mechanism here is actually handling both the cross-attention between target and the input and self-attention, sequence learning within each. So that's the causal attention. And then as I mentioned, the output is a sequence. And then the key design features are self-attention is serving both roles. And we are, in some sense, sharing the parameters between input and target. So same set of parameters are applied to both input and the target sequences. So this is the decoder only.
What is
now
Juneteenth?
We will go into the comparison. So I think there are many, they look very different, at least on the schematics. So how different are they actually? And I argue that they're actually quite similar. And so to illustrate that, we're going to transform starting from this encoder-decoder, which has more structures built in, and then into the decoder-only architecture, and see what are some of the differences.
Is that black
and then
English
interpret
contraction
those differences,
or
those additional structures, are they relevant
the month
nowadays,
June
now
and
that we
date
have more compute,
19th.
better algorithm, and so on.
Date of June 19,
So let's have this table,
1865,
four
when
differences.
enslaved
We'll
people
see
of
each of
African
them, and
descent
then as we go
located
through,
in
we'll
Galveston,
populate this
Texas,
table. So let's
finally
first look at
learned
this
of their
additional
freedom
cross-attention.
from, oh my
What that
god,
means
that's
is that
so nice.
this
Freedom
on the left is
from
an encoder-decoder,
the
which has
slavery
this additional
system.
red block, the cross-attention.
It's not the day
compared
like
to
the
simpler one
fight,
that
it's the
doesn't
day
have
that all
So
like the last
we
people
want to make the
like,
left
get to know
closer
that
to the
there
right.
is no
That
slavery
means we
anymore.
need to either get rid of it or something. And attention mechanism has kind of the four projection matrices. And so self-attention and cross-attention actually have the same number of parameters, same shape. So we can just share them. So that's the first step, share both of these. And then it becomes mostly the same mechanism. And then, so that's the first difference.
Wait a second. Okay, this is so good, but why should we close the gym for Juneteenth? Dude, actually, it is the day that you want to open the gym because we don't want to be a slave to our body anymore.
Separate cross-attention or self-attention serving both roles.
Sorry.
Second difference is the parameter sharing. So what
We
that
want to
means is that
celebrate
between
Juneteenth
the
in
input
gym.
and the target, encoder-decoder architecture uses a separate parameters. And decoder only has a single stack, so it uses the share parameter. So if we want to make the left close to right, we want to share the encoder parameters. So let's do that. I just color this. So now they share the parameters. Third difference is the target to input attention pattern. So we need to connect the target to the input, and how is that done? In the encoder decoder case, we had this cross attention, and then in the decoder only, it's the self attention doing everything. What the difference is that we have this every layer of the decoder attending to the final layer output of the encoder. Whereas if you think about this decoder, it's actually per layer, within layer, when we are decoding.
And also it says something beautiful, right? Like now we can say, oh, decoder only is good, and it happened to in my research multiple times. And about the first like plot that he showed, that we need to remove those structures. We need to remember that those beginning steps were necessary, like practically at least necessary to get to that level. If we didn't have this encoder-decoder system, probably we will never get to the decoder system, decoder-only system. Now we are saying this is boring, but at its time it was really the only way to get to that decoder-only system was going and finding encoder-decoder first. Then we try to make it better. So don't be mad at the beginning stage. This is just study the change.
Say word DOS, we are looking at the same.
Yeah, I should not be mad at game theory. Well, it helped us. Now we have some intuition how it works. Now we have more data. We should put game theory probably aside. If it stops working, if it's not working, well, go find what really works.
A representation of the encoder. And that's
what
within layer.
Why
and I
we
think
should
this is
contact
So
Diego.
if you want to make this close to that, we have to bring back this attention to each layer. So now layer 1 will be attending
Smart.
to
I
layer
love
1
that I
of
watched this video.
And that's then finally, the last difference is the input attention. I mentioned about this bidirectional attention, and because we have this decoder only, typically with the unidirectional attention, we need to make them matching. So we can just get rid of it. I just got rid of some of the arrows. So then at this point, these two architectures are almost identical. There's a little bit of difference in the cross attention, but same number of parameters. And if you have in deep learning, if you just train these two architectures in the same task, same data, I think you'll get pretty much within the noise, probably closer than if you train the same thing twice. So I would say they're identical. And so these are the main differences. Now we'll look at what are the additional structures, what they mean, what that means. So yeah, that's the populated table now. And then, so we can say that encoder-decoder compared to the decoder-only architecture has these additional structures, inductive biases built in.
Mm-hmm.
So let's go into each of them. The first one is what encoder-decoder
The
tries
structures that you want to
each of
remove.
them. The first one is what encoder-decoder tries added as a structure is that input and the target sequences are sufficiently different that it'll be useful to use as separate parameters. That's the assumption. And so why is that useful? When can that assumption be useful? And one example is machine translation. Back when the transform was introduced in 2017, translation was a really popular task. And it was difficult, considered difficult. And because it's just sequence to sequence, and you can actually have a blue score, which is heuristic-based method that can give you a single number, and then people can optimize that. So in that task, we have this input and target in completely different languages. So if the goal is to learn translation only, then it kind of makes sense to have, okay, this parameter in the encoder will take care of the English, and this parameter in the decoder will take care of the German. That seems natural. And what about now? Modern language models is just about learning knowledge. And it's not just about translation, or not even about language. Language just comes up as a byproduct of doing this next token prediction, not even language.
Wow, that was interesting. Okay, let me just check if the gym is open or not. I don't have anything. Dude. Oh, okay.
That seems natural. And what about now? Modern language models is just about learning knowledge. And it's not just about translation, or not even about language. Language just comes up as a byproduct of doing this next token prediction, and translation as well. So does it make sense to have a separate parameter for this kind of situation now? Like, we have some knowledge in German, some knowledge in English, and we, if anything, we want to combine them, and if we represent them in separate parameters, I don't think that's natural. So I would say with this much more general, larger models that can do a lot of things, this assumption seems very unnatural to me. Second example is...
Wow, dude. Very unnatural to you, bitch. Alright, I get it, but okay, don't talk like I'm...
A little bit more modern. 2 years ago when I was at Google, and with Jason, we did this instruction fine-tuning work. And what this is you take the pre-trained model and then just fine-tune on academic data set and so that it can understand the natural language instruction. So the detail doesn't matter, but here let's think about the performance gain by doing this fine-tuning on 2 different architectures we tried. So first 5 is the Flan T5, which is T5 based, which is encoder-decoder architecture. Last one, the latter 5, decoder-only architecture based on POM. So we spent 99% of the time on POM, optimizing a lot of these. And then at the end, we just spent like 3 days on T5. But the performance gain was a lot higher on this. And I was really confused about this, and in a very good way. And after the paper was published, I wanted to dig a little bit deeper into why this might be the case. So my hypothesis is that it's about the length. So academic data sets we use like 1,832 tasks, and here they have this very distinctive characteristic where we have a long input, in order to make the task more difficult, but then we cannot make the target long, because if we do, there's no way to grade it. So there's fundamental challenge of that. So what happens is you have a long text of input and then short text of the target. And so this is kind of the length distribution of what went into the Flan fine-tuning. So then you see this, you have a very different sequence going into the encoder as an input, and a very different type of sequence going into the target. So now this encoder-decoder architecture has an assumption that they will be very different. That structure really shines because of this. It was a kind of an accident, but that was, I think, why this really architecture was just suitable for fine-tuning with the academic data sets. What about now? Do we care about this kind of assumption? And if you think about the general use cases of language models nowadays, if anything, the more interesting cases involve longer generation, longer target. Just because we cannot grade them doesn't mean that we are not interested. Them. Actually, if anything, we are more interested in that. So now we have this like longer target situation. So this separate sequence length parameter doesn't seem to make much sense. And moreover, we think about this chat application, like ChatGPT, we do multi-turn conversation. And then, so what is a target of this turn becomes the input of the next turn. And then my question is, does that make sense to even think about a different parameters if next turn is going to be the same thing? So that was the first inductive bias we just mentioned. And then the second structure is that target element can only attend to the fully encoded ones, the final output of the encoder. And let's look at this additional structure, what that means. So as I mentioned, we have this very top layer attending to it. And so in deep neural nets, typically we see that the bottom layers and the top layers encode information at a very different level, meaning that, for example, in computer vision, bottom layers encode something like edges, top layers, higher levels, combining the features, something like cat face. And so we call this deep learning a hierarchical representation learning method. And so now the question is, if decoder layer 1 attends to encoder final layer, which probably has a very different level of information, is that some kind of an information bottleneck, which actually motivated the original attention mechanism? And in practice, I would say, in my experience, doesn't really make any difference.
Can decoder only attending to the final layer of encoder be an information bottleneck? Oh, we want to see which part of this structure we can remove if encoder is sufficient.
And that's because my experience was limited to, say, 24 layers of encoder of T5. So layer 1 attending to 24, probably fine. But what if we have 10x or 1,000x more layers? Would that be problematic? I'm not really comfortable with that. So I think this is also unnecessary design that maybe we need to revisit. Final structure we're going to talk about is the when we do this, there's like a bidirectional thing in the encoder decoder. Let's think about that. So yeah, bidirectional thing in the encoder decoder. Let's think about that. So yeah, bidirectional input attention, is that really necessary? So when we had this BERT, B in BERT stands for bidirectional.
Okay, why do we also one other thing to remember? He said, we don't know how, we try to build these AI machines the same way as we think. Well, it's good at the beginning because it gives us some intuition, right? But we actually don't know how we think. Like, we don't know how we think. So we just have an intuition of how we think. And we build this AI model based on those intuition. Then it comes to a point that this intuition becomes a bottleneck and we need to remove it. I see.
2018, when we were solving that question answering squad, actually it was a very difficult task. So if you have any additional trick, it can make a huge difference. Bidirectionality was a really useful, like I think maybe boosting up the squad score by like 20. So it was really a huge thing. But at scale, I don't think this matters that much. This is my highly anecdotal experience. So we did, in Flan 2, we tried both bidirectional and unidirectional fine-tuning. Didn't really make much difference. So, but I want to point out this bidirectionality actually bring in an engineering challenge for modern multi-turn chat application. So at every turn, the new input has to be encoded again. And for unidirectional attention, it's much better. So here's what I mean by that. So let's think about this more modern conversation between user and assistant. How are you, bad, and why? And so here, if we think about the bidirectional case, we will, and when we generate bad, we need to encode this input with the bidirectional thing, which is fine. And then after the bad is generated, when we're trying to generate y, we'll need to encode how again, because how can attend to bad, so we need to do everything from scratch again. In contrast, if we do unidirectional one, we can do much better, because now when we are trying to generate y, we don't have to redo how, because we cannot attend to the future tokens, so we don't have to do anything. So if you see the difference, this part can be cached, and then this part is the only thing that has to be encoded again. So this kind of makes a big difference when we think about multiple turns going in. So I would say bidirectional attention did well in 2018, which is mostly solved by scale. And now, because of this engineering challenge, we don't really need that. So to conclude, we have looked into this driving force, dominant driving force governing this AI research, and that was this exponentially cheaper compute and associated scaling effort. And so to understand this driving force, we analyzed some of the additional structures added to the encoder-decoder compared to the decoder only, and then thought about what that means from the perspective of scaling. And I wanted to just conclude with this remark. So we have looked at these kind of analysis, which are all, one can say this is just historical artifacts and doesn't matter. But if you do many of these, now you look at this current events, you can hopefully think about those in a more unified manner and then see, okay, what assumptions in my problem that I need to revisit, and are they relevant? And if not, why? And you have an answer to it. Can we do it with a more general thing and scale up? And so I hope you can go back and really think about.
Damn, this is interesting. Their paper is just... Where is it published? I want to publish this kind of paper. In Nature, fucking Nature. They don't have one line of mathematics. Good job. Wait, guys. That was a nice video to watch, but it means we lost some time. That's why it's stupid to get ready for interviews, because these are now all old. You may not need to learn them anymore. Okay, let me close the curtain here. Game theory. You have data. Fuck game theory. It was not the first time. Now we know how people game. Now we need to learn people. I'm not gonna publish any game theory anymore for a while.
Helicopter in the simulator, or really any robot in the simulator, we often add a lot of noise to the simulator, because one of the lessons we've learned is that if your simulator is noisy, because simulators are always wrong, right? Any digital simulation is only an approximation of the real world. So we tend to add a lot of noise to all of our simulators, because we think that if a learning algorithm is robust to all this noise you've thrown at it in simulation, then whatever noise the real world throws at it, it has a bigger chance of being robust too as well. And so we tend to throw a lot of noise into our simulators. And so one case where that does happen is when we find we threw too much noise at it in simulation. And then that might be a sign we should dial back the noise a bit. Yeah. All right, cool. Yeah, right. So this first diagnostic tells you should work on improving simulation. But just, I think if there's a big mismatch between simulation performance and real world performance, that's a good sign that, that you should improve the simulation. Second, this is actually very similar to the diagnostic we use on the SPAM, Bayesian logistic regression, SVM example. So what we're going to do is we're going to measure this equation. And this is very similar to our previous equation, which is take the cost function, similar to the previous example. Take the cost function j that reinforcement learning is told to minimize, right? J of theta was a squared error, right? So take the cost function that reinforcement learning was told to minimize and see if the human achieves better squared error than the reinforcement learning algorithm, right? And just see, the human flies better, so let's measure the human performance on this squared error cost function and see which one does better. So there are two cases. That equation will be either less than or it'll be greater than or equal to. Right? So less or greater or equal to. So case one is say the
Nothing
human
good
is less
when
than.
it is addictive. I don't want to learn too much.
J of theta human is less than J of theta RL.
Well,
That
what
would be
is the
this
point
case.
of learning being addictive?
Then that tells you
want
that
to
the
learn
problem
1 hour a
is with
day,
the reinforcement
something
learning
like that.
algorithm, right? That
Enough.
somehow the human achieves a lower squared error,
Addictive.
and so the learning algorithm is not
What it
finding
means, what it
the
means
best
is like
possible
it's
squared
making
error.
learning
There's some other
interesting.
controller, as evidenced by whatever the human is doing, that actually achieves a lower cost function, right? So in this case, we think the learning algorithm, our reinforcement learning algorithm is not doing a good job minimizing that, and we'll work on the reinforcement learning algorithm. The other case would be if the sign of the inequality is the other way around, right?
What is the next
Now,
lecture
in
page?
this case,
Expectation
you can infer that
maximization
the problem is in
algorithm.
the cost function, because what happens here is
EM
the
algorithm
human is
and
flying
factor
better than
analysis.
your reinforcement learning algorithm,
Independent component
but the human
analysis
is
and
achieving what
RL.
looks like a worse cost than your reinforcement learning algorithm.
Markov decision process, value
So what this
policy.
tells you is that minimizing J of
Continuous
theta
state
does not
NDV.
correspond to flying well, right? Your learning
Linear
algorithm achieves a
dynamics.
better value for J of theta. J of theta RL is actually smaller than whatever human is doing. So the reinforcement learning algorithm, as far as it knows, is doing a great job because it's finding a value of theta where J of theta is really, really small. But in this last case, you know that finding such a small value of J of theta doesn't correspond to flying well because a human doesn't achieve such a good value in the cost function, but the helicopter actually just looks better or is flying in a more satisfactory way. And that tells you that the squared error cost function is not the right cost function for what flying accurately means, right? And so through this set of diagnostics, you could decide which one of these three things, improving the simulator, improving the RL algorithm, reinforcement learning algorithm, or improving the cost function is the thing you should work on. Right? And what happens and actually in this particular project, and what often happens in machine learning applications is you run the set of diagnostics, and this actually happened when we're working on this helicopter. We run the set of diagnostics, and then 1 week we would say, yep, the simulator's got a problem, let's work on that. And then we'd improve the simulator, and after a couple of weeks of work, we'd run these diagnostics and say, oh, it looks like the simulator's not good enough, and maybe there's a problem with the RL algorithm. Then we work on that, improve that. And after a while, we'll say, oh, looks like that's also good enough, and the problem is in the cost function. And sometimes the location of the most acute problem shifts, right? After you've cleared out one set of problems, it might be the case that now the bottleneck is the simulator, right? And so I often use this workflow to constantly drive prioritization for what to work on next, right? And to answer the question just now about how do you find a new cost function, it turns out finding a new cost function is actually not that easy. So actually one of my former PhD students, Adam Coates, through this type of process realized that finding a good cost function is actually really difficult because if you want a helicopter to fly a maneuver, like fly at speed and then make a bank turn, right? Like how do you mathematically define what is an accurate
Actually,
bank?
all the bullshit I said, I don't like game theory and stuff. That's right. But if I didn't do game theory, I wasn't this at this point. I want to mention this too. I say it now because now I've worked with it and I think it's not working. If I didn't do that, I would say, oh, game theory is so amazing, it works, and I'm not working with it. Now I'm not impressed by it anymore because I'm involved with it.
turn. It's actually really difficult to write down an equation to specify what is a good wave, how to fly like that, and then do a turn. It's just, how do you specify what is a good turn? So he wound up writing a research paper, one of the best application paper more than ICML, on how to define a good cost function. It's actually pretty complicated, but the reason he did it, and it was a good use of his time, was running diagnostics like these, which gave us confidence that this was actually a worthwhile problem, and that resulted in, making real progress in helicopter in the end. Okay. Any questions about this? Actually, I think I've, all right, fun helicopter videos. No, let's not show this, it's fine. You guys saw some of these earlier. All right, so,
do these fake accounts, what are they?
One time. Yeah, all right, let's go through this.
Zuckerberg, remove the fake accounts.
In addition to these specific diagnoses of bias versus variance and optimization algorithm versus optimization objective. When we do RL, I want to just go through that example one more time. So you see everything we just saw again after you learned about reinforcement learning later in this quarter. Okay. Now, in addition to these type of diagnostics, how to debug learning algorithms, there's one other set of tools you find very useful, which is error analysis tools, which lets you figure out, which is another way for you to figure out what's working, what's not working, or really what's not working in the learning algorithm. So let's go through a motivating example. So let's say you're building like a security system. So when someone walks in front of a door, you unlock the door knob based on whether or not that person is authorized to enter that place. And so let's say that so there are a lot of machine learning applications where it's not just one learning algorithm, right? But instead you have a pipeline of stringing together many different steps. So how do you actually build a face recognition algorithm to decide if someone approaching your front door is authorized to unlock the door, right? Well, here's something you could do, which is you start with the camera image like this, and then you could do pre-processing to remove the background. So all that complicated color background, let's get rid of that. And it turns out that when you have a camera against a static background, right, you could actually do this with a little bit of noise, but relatively easily. Because if you have a fixed camera that's just like mounted, on your door frame, it always sees the same background. And so you can just look at what pixels have changed and just keep the pixels that have changed compared to, right, because, this camera always sees that gray background and that brown bench in the back. And so just look at what pixels have changed a lot and that's background removal, right? So this is actually feasible by just looking at what pixels have changed and keeping the pixels that have changed relative to the background. And so after getting rid of the background, you could run the face detection algorithm, and then after detecting the face, it turns out I've actually worked a bunch on face detection, built a bunch of face recognition systems. It turns out that for some of the leading face recognition systems, depends on the details, but some of them, it turns out that the appearance of the eyes is a very important cue for recognizing people. This is why if you cover your eyes, it's actually a much harder time recognizing people, as eyes are very distinctive of people. You can segment out the eyes, segment out the nose, another thing, segment out the mouth. Hey, it's Halloween. And then feed these features into some other algorithm, say registry regression, that then finally outputs a label that says, is this the person, right? That you're authorized to open the door for. So in many learning algorithms, you have a complicated pipeline like this of different components that have to be strung together. And if you read the newspaper articles about, or if you read research papers in machine learning, often the research papers will say, oh, we built a machine translation system, we trained it, and we
Okay, what about eyes?
You can set the algorithm, right? But instead, you have a pipeline of stringing together many different steps. So how do you actually build a face recognition algorithm to decide if someone approaching your front door is authorized to unlock the door. Right? Well, here's something you could do, which is you start with the camera image like this, and then you could do pre-processing to remove the background. So all that complicated color background, let's get rid of that. And it turns out that when you have a camera against a static background, right, you could actually do this, you know, with a little bit of noise, but relatively easy. Because if you have a fixed camera that's just like mounted, you know, on your door frame, it always sees the same background. And so you can just look at what pixels have changed and just keep the pixels that have changed compared to, I mean, right, because, you know, this camera always sees that gray background and that brown bench in the back. And so you just look at what pixels have changed a lot and that's background removal, right? So this is actually feasible by just looking at what pixels have changed and keeping the pixels that have changed relative to the background. And so after getting rid of the background, you could run a face detection algorithm. And then after detecting the face, it turns out I've actually worked a bunch on face detection and built a bunch of face recognition systems. It turns out that for some of the leading face recognition systems, it depends on the details, but some of them, it turns out that the appearance of the eyes is a very important cue for recognizing people. This is why if you cover your eyes, it's actually a much harder time recognizing people, as eyes are very distinctive of people. You can segment out the eyes, segment out the nose, another thing you segment out the mouth. Hey, it's Halloween.
Are people laughing? It is funny.
Eyes are very distinctive of people. You can segment out the eyes, segment out the nose, another thing you segment out the mouth. Hey, it's Halloween. And then feed these features into some other algorithm, say registry regression, that then finally outputs a label that says, is this the person, right? That you're authorized to open the door for. So in many learning algorithms, you have a complicated pipeline like this of different components that have to be strung together, and. If you read the newspaper articles about, or if you read research papers in machine learning, often the research papers will say, oh, we built a machine translation system. We've trained it on a gazillion, sentences found on the internet, and it does great, and a pure end-to-end system. So that's like one learning algorithm that sucks in an input, like suck in an English sentence and spit out a French sentence or something, right? So that's like one learning algorithm. It turns out that for a lot of practical applications, if you don't have a gazillion examples, you end up designing much more complex machine learning pipelines like this, where it's not just...
Interesting. This video is getting related to what we talked about on the other video, that it's easier to find a model because we are having less assumptions and structures. Because once you have one example, it's just you don't really know what is real, what really matters and what really doesn't matter, and you train your model in a way that adds extra assumption.
Monolithic learning algorithm, but instead there are many different smaller components, and I think I think that I think that having a lot of data is great, right? I love having more data, but big data has also been a little bit overhyped, and there are a lot of things you could do with small data sets as well. And in the teams I work with, we find that if you have a relatively small data set, often you can still get great results. I don't know, my teams often get great results, like 100 images, 100 training examples, or something. But when you have small data, it often takes more insightful design of machine learning pipelines like this. Right?
Because when data is small, it's smarter not to have based on like machine learning. It's better to have. That's what the other video was saying. At the beginning, when the model is small, use just assumptions, use thinking instead of machine learning.
Now, when a machine learning pipeline like this,
keep your tools simple.
The things you want to do, what you want to do
simple.
is, so you build a pipeline like this, and it doesn't work, right? It's this common workflow. You build something, doesn't work, so you want to debug it. So in order to decide which part of the pipeline to work on, is very useful if you can look at the error of your system and try to attribute the error to the different components so you can decide which component to work on next, right? And there's actually I'll tell you a true story. Remember the pre-process background removal step, right? Just getting rid of the background. It turns out that there are a lot of details of how to do background removal. For example, the simple way to do it is to look at every pixel and just see which pixels have changed. But it turns out that if there's a tree in the background that waves a little bit because the wind moves the tree and blows the leaves and branches around a little bit, then sometimes the background pixels do change a little bit. And so they're actually really complicated background removal algorithms that try to model basically the trees and the bushes moving around a little bit in the background. So you know that even though the pixels of the tree moves around, this part of the background, you should still get rid of it. So background removal, there's simple versions where you just look at each pixel and see how much has changed, and they're incredibly complicated
7
versions.
videos to go. Let's finish it.
I actually know someone.
What if one day we say
was
set
trying to
for
work on a problem
binging
like
on
this,
machine learning?
and they decided to improve their background removal algorithm. And they actually, this person actually literally wrote a PhD thesis on background removal. And so I'm glad he got a PhD. But when I look at the problem he was actually trying to solve, I don't think it actually moved the needle, right? This is one of the nice things about academia, because so long as you can still publish a paper, and it was technically innovative. It was actually very good technical work. But if it goes to publish a paper, great, do that. But if it goes to build a better face recognition system, then I would carefully ask which component should you actually spend your time to work on, right? So here's what you can do with error analysis, which is.
It's actually interesting because, based on the last video, we can also say when we want to use our brain or thinking or adding structures and building mathematical models, it's just at the beginning. When we are facing a problem, we don't have data, that's the time we want to use our brain. And in academia, we should not publish paper. We should go after real problems. What is the thing that we cannot do with our tools that we already have, with our machine learning tools? That's the part we need to use our brain. The rest of it, use those tools, take it to the ultimate, leverage them to the ultimate point, and then if you don't know anything else to do, maybe that's the point you need to start thinking.
Say your overall system has 85% accuracy. Here's what I would do. I would go in and in your dev set, in your development set, the Holder cross-validation set, right? Go in and for every one of your examples in the dev set, I would plug in the ground truth for the background, meaning that rather than using some approximate heuristic algorithm for roughly cleaning out the background, which may or may not work that well, I would just use Photoshop. And for every example in the dev set, I would give it the perfect background removal, right? So imagine, rather than using some approximate heuristic algorithm for roughly cleaning out the background, which may or may not work that well, I would just use Photoshop. And for every example in the dev set, I would give it the perfect background
next to each other. It would be decoder only.
Instead of some noisy algorithm.
Dude, I'm connecting the dots. Dude, I'm really smart. I'm really smart. Happy that I think, okay, the other video is published. I think we spent some time on the other video. It was not on the list, but it was good. We learned something, and now we are learning this stuff better.
Right, and then you could give it perfect performance on your dev set and your test set just by using Photoshop to just tell it, this is a background, this is a foreground, right? And let's say that when you plug in this perfect background removal, the accuracy improves to 85.1%. And then you can keep on going from left to right in this pipeline, which is Now,
Dude,
instead
the
of using some
moment
learning
I
algorithm to do
started
face
going from
detection,
left to right,
let's
he
just go
said
in
left to
and for the
right.
test set, modify,
If
kind of have the face detection
I'm not a
algorithm sheet,
miracle,
right? Have it
what
just
is?
memorize the right location for the face in the test set and just give it a perfect result in the test set. So when I shade in these things, that
Dude,
means I'm giving it
shit.
the perfect result, right?
I'm more
So let's
flexible
just go
on
in
this
and on
side.
the test set, give it the
Easily.
perfect face detection for every single example, and then look at the final output
Yeah,
and
this
see
way
how
I'm
that
much more
changes to
flexible.
see the final output, right? And then same for these components, eye segmentation, no segmentation, mouth segmentation, and you do these one at a time. And then finally, for logistic regression, if you give it the perfect output,
Give it to me.
your accuracy should be 100%, right?
100%.
So now, what you can
Now,
do
right
is
now.
look at the sequence of steps and see which
Take a
one
step.
gave you the biggest gain. And it looks
I
like,
like gains.
in this example,
Gains.
it looks like when you
have a
gave
pump.
it perfect
Kickboxing
face
is
detection,
closed.
the accuracy improved from 85.1 to 91%, so roughly a 6% improvement. And that tells you that if only you can improve your face detection algorithm, maybe your overall system could get better by as much as 6%. So this gives you faith that maybe it's worth improving on your face detection component. And in contrast, this tells you that even if you had perfect background removal, it's only 0.1% better. So maybe don't spend too much time on that. And
8 minutes
like
to
that,
go.
when you gave it perfect eye segmentation, it went up another 4%. So maybe that's another good project to prioritize, right? And if you're in a
But we
team,
don't know
one
how to
common structure would be
prioritize
to do this type of
unless
analysis
we have
and then have some people
experience
work on
or
face detection, some people work on eye
we
segmentation.
do it
You could
first and
usually
say,
do a
oh,
few
it
things in
didn't
parallel
work,
if you're a
let's
large
try
team.
something new. Let's
But at
try
least this should
something
give
new.
you a
Let's try
sense of
something
the
new.
relative prioritization of the different things. This question?
Did you do this cumulatively or
Question.
make the eye segmentation perfect and then kind of go back and now the eye segmentation is not perfect anymore and now you fix the nose segmentation or you kind of add each property to the
Yeah, right. So do you just cumulatively, such as give it perfect eye segmentation, then add on top perfect nose segmentation, or do you give it perfect eye segmentation, and then take that away, and then give it perfect nose segmentation? The way I presented it here is done cumulatively, and it turns out that, let's see, if you give it, once you give it perfect face, once you give it, perfect things in the later stages, maybe the earlier stages doesn't matter that much anymore. So that's one pattern. But it turns out that you could do it either way, right? For the eyes, nose, mouth, you could do
Order
it cumulatively
doesn't matter?
one
I
at a
think it
time,
matters.
and you'll
at
probably
the end
get
it works.
relatively similar results.
So order in
no
general
guarantee. You might
doesn't
get different
matter.
results in terms of conclusions, but I think to the extent that you are wondering if doing it cumulatively versus non-cumulatively might give you different results, I would just do it both ways, and I think these error analysis is not a hard mathematical rule. If that
Yes!
makes sense. It's not
Experience.
that you do this and then there's a formula that tells you, okay, work on face detection.
It's just
I
trial
think
and
that
error,
this should
trial
be,
and error,
an
trial
area
and
of
error.
judgment
Thomas
on,
Edison,
you know,
trial and error.
how
Thomas
hard do you
Edison,
think it is to
trial
improve
and
face
error.
detection
Thomas
versus
Edison,
eye
trial and error.
segmentation, right? But this at least
Thomas
gives you a sense of it gives you a sense of prioritization. And it's worth doing this in multiple ways if you think that if you are concerned about discrepancy between the cumulative and non-cumulative versions. Right? So whenever you have a complex machine learning pipeline, this type of error analysis helps you break down the error to attribute the error to different components,
What are
which
the
lets you
odds
focus your attention on what to work
I
on.
can stabilize it before the video finishes.
detection perfectly and the accuracy actually dropped. What that indicates.
Oh, right, yeah. If you do face detection accuracy and then your error drops, what does that indicate? It's not impossible for that to happen. It would be quite rare. I would, so at a high level, what I would do is go in and try to figure out what's going on, actually. I wouldn't ignore that. So
So if it's going this way,
sometimes the
it
team
means
gets
that I have
discovers
to-
a weird phenomenon like
First
that,
of all,
and
let's
just ignore it and
fix
move on. I wouldn't do
this
that. I would. It's actually
issue.
go. Whenever you find one of these
So
weird things,
this
I wouldn't.
this means that I
gloss over
need
it
to
or
bring
ignore
more
it.
weight
I
on
would
the
go in and
left.
figure out what's going on.
Maybe I
Does it make
want
sense?
to
It's like
change it
debugging
this way,
software.
so it's
You know,
moving
if
this way.
you're trying to debug a piece of
That's close.
software and if whenever you move your mouse over, some button, some random pixel color changes, you go, that's weird. And then some people just ignore it. It's like, oh, well, the user won't see this. But so, let's go figure it out, right?
What?
See changes, you go, that's weird. And then some people just ignore it. It's like, oh, well, the user won't see this. But so, let's go figure it out, right? So what you're saying is quite rare, but not impossible. But I don't have an easy solution for how to figure out what's going on, but I would want to figure out what's going on.
I like machine learning.
So one last thing before
That's
we break.
nice.
So error analysis helps figure out the difference between where you are now, 85% overall system accuracy, and 100%, right? So it tries to explain
That
the
was the
difference
snap
between
that made it fun.
and perfect performance. There's a different type of analysis called ablative analysis, which figures out the difference between where you are and something much worse. So here's what I mean. So let's say that you build let's say you build a good anti-spam classifier by adding lots of clever features to the regression, right? So spelling correction, because spammers try to misspell words to mess up the tokenizer, to make words look, spammy words not look like spammy words. Single host features, what machine did the email come from? Email header features, you could have a parser from NLP, parse the text, use JavaScript parsers to understand, right? Or even can fetch the web pages that the email refers to and parse that. And the question is, how well did each of these components really help? And it turns out, if you're writing a research paper, sometimes you write a research paper and say, hey, look, I built a great spam classifier, and that's okay. That's like a nice result to have. But if you can explain to your reader, either in a research paper or in a class project report, like a term project, what actually made a difference, that conveys a lot of insight as well.
The odds are one.
So say simple logistic regression.
One!
With all these clever features,
I
got
made
94% performance. And with all of your addition of all these clever features, you got 99% accuracy. So in ablative analysis, what you would do is remove the components one at a time to see how it breaks, right? So just now we were adding to the system by making components perfect with error analysis to see how it improves. Here we're going to remove things one at a time. Oh, did not mean to remove that. Let's see, let's figure out what's going on with PowerPoint. All right, remove things one at a time to see how it breaks. So let's see, remove spelling correction. And as a set of features, the error goes down like that. Then let's remove the sender host features, remove the email header features, and so on, until when you remove all of these features, you end up there. And again, you could do this cumulatively, or remove one and put it back, remove one and put it back. Or you could do it both ways and see if they give you slightly different insights. And so the conclusion from this particular analysis is that the biggest gap is from the text parser features, because when you remove that, the error, the accuracy went down by 4%. And so
you wanted to
this is strong evidence. If you want to publish a paper, you could say, right, text parser features significantly improves spam filter accuracy, and then that level of insight. And then if you're working on a spam filter for many years, right, there are really important applications where sometimes the same team will work on for many years. So this type of error analysis gives you intuition about what's important and what's not, and helps you decide to maybe even double down on text parser features, or maybe if the sender host features is too computationally expensive to compute, it tells you maybe just get rid of that and without too much harm. And also, if you're publishing a paper or sending a report, this gives much more insight to your report. Okay? All right. So that's it for error analysis and ablative analysis.
Lecture 13 was nice. I like it.
Class projects as well. I'll take one last question now, right?
How would you choose the order in which to remove features?
Oh, yeah.
Order doesn't matter.
How would you
Because
choose the
we
order?
don't know the order right
No
away.
systematic way. If you can have a systematic way, you do that. The other way, the non-cumulative, where they remove one, put it back, remove one, put it back. So either way works. All right, let's break. And problem set 2 is due tonight, friendly reminder, and problem set 3 will be posted in the next several tens of minutes. Okay, thanks everyone.
Thank you. Alright guys, thank you too. I like both videos. It was cool. And I don't want to play counter anymore for today.